right, it's the lecture you've been waiting for, the last one of the semester, allowing you to say that I made it through high school chemistry. So here we are going to continue. We left off on number 72, and the concept here is going to be one of these metathesis reactions, also called exchange reactions. One of the things that's kind of interesting about these reactions, go ahead and write that whole reaction out there, is that they aren't redox reactions. There's no loss or gain of electrons. So what you have to be able to do one of these reactions is add an AQ or an S symbol. So each one of these is either aqueous, meaning it dissolves in water, or it's a solid, meaning it doesn't dissolve in water. So how do we know that? How do we know what dissolves in water and what does not? Well, that is on the back of your yellow sheet. Okay, so we'll just go through these one at a time. This is, and you use the anions will be the most helpful to you. Nitrates, there's a rule. Rule number 1 says all nitrates are soluble. So therefore, that one is going to be an AQ. And you notice it even says that at the top in case you get stuck. The ones that are soluble are going to be aqueous. Now, KCl. We've got to find a rule that has chlorides. There it is. Rule number 5. Most compounds containing chloride are soluble. Now, this is not one of the exceptions. If you look over to the right side, there are 3 exceptions to chlorides being soluble. So this one is going to be soluble. It's not an exception. As a matter of fact, those family 1 compounds are almost always soluble, no matter what the negative ion is. So, yeah, this guy's going to be soluble. So that would be an AQ symbol as well. This one, if you remember what we just talked about, rule number 5, the exception is AgCl, also mercury chloride and lead 2 chloride. Those would also be exceptions, but this one certainly is an exception, and so this blue compound would be a solid. And then if you remember rule 1, all nitrates are soluble, so you just plug in the aqueous and solid symbols. So really this is just ions floating in a beaker, and what happens is when you put those 2 solutions together, they will form a new substance with new properties, being a solid. So, but you didn't really exchange any electrons. There was no fancy bonding involved, just some subtle things like hydrogen bonding and forming the solution and things like that. And of course this new ionic bond that forms, making the solid of the compound. So if you use your solubility rules and check out all the possibilities and see which ones are soluble, and the question actually asks which one would not have a precipitate, which really means that you wouldn't see any change in the reaction. So there's one where it's all aqueous, and it's up to you to find that one using your yellow sheet. Okay, so another problem that you can definitely do. Number 73 is about Le Chatelier's principle, which if you watch the video on it, you're going to be in good shape. I'll just clarify that it's a little bit different than the one in the video in that they don't say directly what they're adding, but if you have liquid HCl in equilibrium, and that's what that double arrow means, and you add NaCl, you're really adding just this. So what happens to the equilibrium system when you add one of those products? Rewatch the video if you have to, but that one will be slam dunk if you take the hint that I just gave you. Alright, so number 74 is talking about phosphoric acid. I put the psychedelic acid background on there because it's an acid, man. Cool, like from the 60s. So what is phosphoric acid? Well, the structure of it is H3PO4. Now, if you draw it out this way, from everything we learned in organic chemistry, and this is, chemistry, you would start this way, and you would say, this is working out really well. You've got these 3 OHs. Each oxygen has 2 bonds, and the phosphorus has 4 bonds. That's 2, 4, 6, 8 valence electrons. All is right with the world. However, there's a little bit of a problem right here. Oxygen should have 2 bonds. So the actual structure of phosphoric acid is, that's 5 bonds. That's more than the stable octet. Now, when you take AP chemistry, a couple years from now, you will get a good explanation of how that happens. But for now, you can just go ahead and just be horrified that this could happen. It's just terrible. So it's just sort of a sad thing. But phosphorus can do that. And as there are actual several examples, and there's even 6 bonded compounds. So that stable octet was a tiny little lie that I told you. But this is a really good example. And those of you who are biologists go, is that the same that's in a phosphate group? And I would say, yes, it is. Okay, that phosphoric acid makes the phosphate in the DNA. And if you made a DNA strand ever, that's the P that you probably put in there is this derivative of this. Now, it'll give up one of its hydrogens. If it's an acid, it can give up one of its hydrogens. When it does that, if this has a negative charge on it, then we're cool, because that means it just has that extra pair of electrons. So this is how this compound can act as an acid. And you might want to redraw that in your notes and say, here it is before, and here, this is why we call it phosphoric acid, man, because it can donate a hydrogen. Okay, so that H plus breaking off, and that's just the first time. The second one, it could break off a second and even a third. But this can form 2 nice little bonds, like in the DNA. When you have the sugar, the phosphate, and the base, it does that quite nicely. All right, so get that structure, and I think you're going to get that one right as well. For 75, this is just sort of like a fun fact. Okay? Every bit of water that you drink has acid and base in it. And if you multiply their concentrations together, you get 10 to the minus 14th. That's a really small number. Okay? You can call that 1 times 10 to the minus 14th if you want. But if you know this equation, they're going to give you one of these, and then you solve for the other one. You know it has to equal 10 to the minus 14th whenever you multiply those two together. So, fun fact, water is an acid and a base. Really weak, but they add up. And if this is a neutral solution, then these are 7, and that's not a coincidence that that's a pH of 7. And that the pH scale is 14, because it just does a fancy math thing. And that's why it's a 14-point scale, because that 10 to the minus 14th for water. Number 76, a little bit of a tricky one here. If you have 1 molar concentration of NH4,3N, the actual concentration of the NH4 is 3 times that amount, because there's 3 of these, and then you would have 1 molar concentration of the nitrogen. It's an important concept, and it's definitely something that can happen. If you think about it, if you have 1 car, you have 5 tires, including the spare. It doesn't mean it's just a smaller part of your car. So that's what this is referring to. So that'll really help you there. Number 77, you know that the equilibrium constant is products over reactants. So, and this is for an acid. It's called Ka, and it's special for an acid. If it's large, if it's a bigger number, that means you have more product and a stronger acid. So get the notes down for that. And then you got number 77. You'll be able to reason that one out. The largest Ka value is the strongest acid. This should look familiar to you. Ma, Va, Mb, Vb. We did that in an earlier part of the test. And that's acids, base, molarity, volume. Okay. I'm going to grab something for this part. The C-Rex rocking the safety goggles for this part. Okay, so hit the pause right now and draw that molecule as is. Okay, welcome back. Now, what you have right there is something called phenolphthalein. All right, so go ahead and write that out, get the spelling. But this is one of those indicators that changes pH. And when it is in this form, it's clear. So this has phenolphthalein in it, and it's an acid. Okay, so it means that it has these hydrogens. Now these hydrogens can actually be kind of ripped off of there, and that happens when you add a base to the solution. Okay, so when I add a little bit of base here, you can see there's a color change, and it goes to being a different color. And here's what's happening chemically. You can just kind of show that, cross it out, or redraw the whole molecule. Hit pause and redraw the whole thing. But that is a phenolphthalein without hydrogens. Okay? So you might be asking, can we put the hydrogens back on there? So of course that's pink in color when the hydrogens are gone. Can we put the hydrogens back on there? Answer, there's your acid. Flop that in there. Whoops, it's not as strong as the base. So let's give it a try here. And there you go, back to clear. Okay, and that's just because you just added those hydrogens right back on there. Okay, and that's number 79. Pink when it's a base, and clear when it's an acid because of the gaining and losing of those hydrogens. All right, the last one is something that we covered, I think, fairly well, and that is electrochemistry. So I'm going to have you write these equations down, and we're going to do one of these E0 cell problems that we've done before. So get that all written. And this is actually a really easy problem to do if you just remember one thing. You have to find the smallest number and flip the sign. Okay? See what I did there? That's the smallest number, and I flipped the sign, and that's the E0 ox. You probably remember doing these types of fun. So the smaller one, flip the sign, don't do anything to the bigger one, add them up, and then you will get the voltage for that battery. You remember we did that thing where we made batteries and competed on that, and that was kind of fun. So anyway, that's our review. Thank you for a very interesting and unique semester. Bye.